Hello everyone. In this video and the next video, I'm going to talk about nonlinear simulations in ANSYS. In general, the sources of nonlinearity in simulations are large deformations, which is kind of also related to nonlinearity in material, and then the changes in the context or topology of the problem. The large deformations, we talked about it in a few of the previous videos and turning on the large deformations. What I want to talk about in this video in the changes in the contact surfaces, and the other one is going to be in the next video, nonlinearity in material. So the problem that we are going to look at is these plastic snaps, right? That you have this basically insert and you push it down inside these prongs and it's gonna lock, right? So it's this locking mechanism, the snapping lock that we have made of plastic. And the thing is, the surfaces, the contacts are going to change, right? In the beginning, you only have a small contact between them. And then you see as the part is inserted, you have more and more surface contacts. And if there is friction also, these two together would definitely add nonlinearities to your simulations. So we are going to look at this problem in ANSYS. So to create these two objects, we need to create this sketch on two separate planes. We create this on, let's say, XY plane, and then we duplicate it again on another sketch. Then we trim the entities. We create these surfaces with 5 millimeter thickness. We apply a plastic material, and then we perform the static structural analysis on it. So this is what we do. We go to static structural, and then the first thing we want to do is we want to add plastic. So we go here, and here we add a material called plastic. Now we can be more specific about it, but for now it's good enough. And we choose it to be from the isotropic elastic material. So we double click here to add that. And then the Young modulus for this plastic is 2.8 e to the 9. And the Poisson's ratio is 0.35. Okay, so we add this plastic so we can use it for the insert and the prong. And then we go to the design modeler and we create the sketch with the dimensions that I showed you. And then we are going to create these two objects, and then we're going to move basically this object to the first situation. So we're going to move it up. And since this problem is completely symmetric, instead of me doing analysis on the whole thing, I'm going to only do analysis on half of it, which you can see here. That makes the problem simpler, and since these objects have a small thickness and uniform, I reduce it down to a 2D plane stress problem, okay, to reduce the amount of complexity on this. So first, let's go ahead and do these sketches together. So what you need to go is you go on the ZY plane and you change your units to mils, and you can start using your polyline command. And here, to save the time of the video, I have created the final sketch, and I show you the sketch with all the dimensions that I have provided here for you. And now I'm gonna duplicate this sketch onto a new one. So you see there is a sketch 1, so I click here and then I create sketch 2, and now I want to copy everything from sketch 1 to sketch 2, so I want to create identical sketches. So first I select the sketch 2, right? Then I go to sketching, then I basically choose the duplicate under modify, and then I box select everything like that. Okay, so everything is box selected, right? And then you right click and say duplicate selection. So now everything from sketch 1 should be duplicated on sketch 2, and we can check that. If I right click here and hide the sketch 1, sketch 2 should be exactly the same as what? Sketch 1 here, as you can see. So I have two identical sketches and they are both fully defined. Now I start what? I start trimming the sketches and I will create the two objects that I have using surfaces. So the first thing, I go to sketch 1 and start what? Start trimming. So I need to trim this object, and the first thing I need is basically the prong. So I get rid of the lines that I do not need, right? And I create this object, and I need two small fillets on these two corners. So I go to fillet, I choose 2 mils, and then I apply it basically here and then here. So now my object is ready except for this extra line here. And now I can go to concept and say surfaces from sketch. And I have already chosen sketch 1, applied, and then I use 5 mils for the thickness. And then now I say generate. And there we go. So this is your what? This is your prong object. And now I can go to sketch number 2, but before that I hide sketch number 1 and I hide this surface body. So I can only work on sketch number 2. So now I go to sketch number 2 and redo this time the trimming and the fillets, but make sure only the top object stays. Okay, so here we eliminate the parts that we do not want, like that. And now this is your insert, and again we need two fillets of 2 mils, and they are going to be applied here and here. And again I go to concept, create surfaces from sketches, I choose a sketch 2, apply 5 mil thickness, and then I generate this object here, this one. Right, so this one is the only thing I need to do is, since these are two separate objects, I want to make sure that I change this add material to add frozen, because I want the two objects to be two separate objects. You see, this is from sketch 2, and let's see now. Here we go. Okay, so now you can go ahead and show the other object, right? So here we go. I have two objects, and they have their own sketches. If you want, you can hide the sketches if you don't need them anymore. Okay, so these are the two objects that I've created, and this is in the lock position. What I want is to lift this up so that this curve here, this curve, and this curve are touching each other. So what I need for that is to translate the surface up enough to have the touch, and the number I found from the textbook, it's about 18.56 mils. So what I need to do is to go to create, and then here go to body transformation and translate it. And what I need is to move this guy up, so I apply it, and then what I need is the coordinates by coordinates, and what I need is in the y direction 8.56 mils. As you can see, it goes up and now it's translated upward. So now this is the position that they start contacting each other, and I start pushing down to lock them together, right? And the other thing I want to do is to give them proper names, right? So here, this guy here is the prong, so I rename it as prong. And the other one is the insert, so I rename it as insert. And my geometry is good to go, so now I close it. And here under this, I make sure my analysis type is 2D, and then go to the model, to the mechanical. So now I'm in mechanical. The first thing I make sure under geometry the behavior is plane stress, which it is. The other thing is I make sure the material for them is not the structural steel but the plastic, right? So I go under material assignment and make sure that they are both made of plastic. And so now my material is good to go. The other thing I want to do is I go to the connections under contacts and see there is a contact region here, which are those two curves, as I said. But since my contact region is going to be expanding to 4 curves, right? I mean, this line here, that fillet, that line, and that curve, and similarly here, the line, the curve, the line, and the curve, I need to change my edges from only what? 1 to what? To several. So here, the contact object is the prong, and the target is what? The insert, right? And so what I want to do for prong, which is the bottom object contact, instead of having one edge, which is this red edge, I want to select all of those 4 edges. So I click here on the contact in the edge area, right? And I select what? This guy, and I make sure here I have edge selection filter. So I choose this, 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 and this. All of these can have contact. So I change it to 4 edges, and similarly, I do a similar thing for the insert. And what I will do, I choose this one, this guy, then this one, and this one. These all can have contacts. So I change them to 4 edges. The other thing is I change my contact from bonded, which means the objects will not move with respect to each other, to what? To they can move with respect to each other. And it can be friction or frictionless or frictional. And here I assume that I do have friction. And I use a coefficient of friction, kinetic friction, and I use, let's say, 0.1, right? So now I assume I can go ahead and apply the mesh. And here, one of the things I want to do is to choose a small mesh size, okay? So if I create a mesh right off the bat, the mesh is not going to be fine enough, and specifically around these contact edges, I need much finer mesh. So the first thing I do, I change this 2 mil to 1 mil, so my mesh is a little bit smaller. And the other thing I do is I go ahead and insert some refinement, and I choose all of those edges that might come into contact, okay? So around these areas, I definitely would need what? Finer mesh, because all of the calculation is done over here. So I choose all of those, and now let's see if I get a better mesh. So this is the mesh with 1 mil, but I reduced it down to 0.5 instead of 1 mil. So around these areas, I really have fine mesh, and I guess this is good now, fine enough mesh for my solutions, and the elements are quadrilateral, which makes the solution converge faster. So now that I have the mesh created, now it is time to what? To set up the analysis. So this is where I am, analysis, right? And I go to analysis solution. And here I'm going to do my simulation in 2 steps. And why 2 steps? In the first step, I push this guy down into it. And in the second, I pull it back up. So I basically lock it and unlock it. And I want to see whether there is a difference in force when you want to lock it or pull it out, if there is any force difference. So instead of 1 steps, I make it 2 steps here. And then since here large deformation is inevitable, so I go ahead and turn it on here. And then I need to here provide my conditions, right? So what I need to do is I have to provide a fixed support here on this edge, because this edge is not going to move. So I fix that edge, it's not going to move. The other thing is I provide frictionless basically support on this edge and this edge. These are the middle of the object, right? Remember, these are on the axis of symmetry, and I apply basically frictionless support over there. And the other thing I need is I apply some displacement on this top edge here, and the X is free, but the Y has to go down for 18.5 mil and then go back to 0. So I'm going to go down and then go up again, right? So since my y is not a constant number, instead of a number, I provide tabular data. So at 0, it's 0. At 1, it goes negative 18.56, the amount that I shifted up. And at 2, it goes back to 0, right? So this is pushing it in and then pulling it back up. Okay, so this is your what? This is your y displacement here. And for solutions, I clearly need to insert a total deformation. And I also need to see how much force I need to put this guy down. I need to find the force I need for that displacement. So I right click here, insert a probe of force reaction, and for the condition here, for the boundary condition, I choose that displacement, okay, that I had. So now it is going to give me the force related to that displacement, basically the amount of force that you need to push down or take off. So the other thing is the force that we need is only in the y direction. So instead of this result selection all, I change it to only y-axis. Okay, because that's the only force that I need, the upward, downward force. That's all I need. Now, since we included friction and we have a two-step solution, as you remember, I need to provide the numbers for the first step and the second step, right? I need to tell it the amount of basically the steps that it needs to take. It's a nonlinear solution. You definitely need to take small steps. Otherwise, your program is not going to converge. So the first thing is, how much is the time for the first part of the solution? I say 1 second, okay? So here for step number 1, let's end it at 1 second. Do you need auto time stepping? Yes. And you control it by times. And I choose 0.01 and a tenth of that for the minimum time step. So these are the conditions that I need for the time step of the first part of the solution, which the insert goes down into the prong. Then I need to provide data for the second time step. So say for the second time step, the final time, let's say 2 seconds. So it takes 1 second to go back up. And again, I make sure that this is on. And the other thing I want to do is this carry over time step. I turn it on. What is this guy? It uses the conditions at the end of this first part of the simulation, at the end of the 1 second. It uses those results as initial condition for the second part of the simulation, right? So whatever condition you have, the nodal displacement, everything, it uses those as initial condition for the second part. Because if you don't, then it assumes that when it starts at second 1 and wants to go to second 2, your object is still up here. So you definitely want to say, hey, carry over time step, yes. Use initial condition of at the end of 1 second for the second part, okay? And here again, you want to change this by time, and you need a minimum time step, and you need some maximum value, and I use the same numbers as I did last time, and 0.01 and 0.1, right? And I guess now the analysis setting is good for solution information. Instead of solver output, I can choose to show me the force convergence, so I can see whether the system is converging or not. And let's see if the system can solve this for me. Okay, so this is the result of the formation, and if you want, you can see here, this is what happened, right? And then this is the force. Because of friction, the plot is asymmetric. And if you can see, the maximum negative force, which is downward force, is about negative 259 Newton. That's the force you need to push it down and lock it. And then the maximum positive force is a little bit over 200, right? You can see it here, right? It's the 204 Newton is the maximum positive force that you need to pull it up. So clearly here, when you lock it, you need a little bit more force than when you pull it out, but the amount of force in both of these scenarios is shown here. So hopefully this video was useful to you, and I will see you in my next video.